Thank you very much, Lynn, and thank you for the introduction. And for all of you for showing up. This is a huge audience. I'm going to tell you about wide binaries. And in particular, I'm going to tell you about some weird wide binaries that were recently seen with GAIA. And I'm going to explain to you how we think they became so weird. So I'm going to start by thanking my sponsors, so Institute for Advanced Study. I also have I'm a visiting lecturer at the University of Oxford. And I also thank Rod Stewart and Tina Turner for providing the title for this talk. All right, so let's get into it. So I'm going to split the talk into 4 parts. And first of all, I'm going to tell you why the binaries are weird, or rather, what we mean observationally that the binaries are weird. And then I'm going to try to actually explain that theoretically. When I say weird, I mean that the binaries have a particular orbital distribution, in particular a certain eccentricity distribution, something that we call a superthermal eccentricity distribution. If you don't know what that means, don't worry, you will know in 5 minutes' time. But that was not expected. Now, it turns out there are 2 things that can produce that dynamically, possibly. One would be the effect of the galactic tide, and one would be the effect of stellar encounters. And I'm going to show you, and I'm actually going to prove in the second and third parts of the talk, that neither of those things can be responsible for producing today's observed distribution. And that leaves us with something where we can say something quite rigorous and I hope important about how wide binaries actually formed in the first place. So that's the plan. So let me get started. Hopefully this works. Yes. So I'm going to really kick off with something that's insultingly basic, kindergarten physics. This is the 2-body problem. Right? So I have a 2-body system, a red star and a blue star, and they're orbiting around each other. And if I just sit in the center of mass frame of the blue star, then the red star moves around it in an ellipse, and the blue star sits at the focus of this ellipse. And the ellipse has a semi-major axis A, so this whole distance across the ellipse here is 2A, right? Something slightly less trivial. Oh, and by the way, the binaries that I'm going to talk about in this talk, when I call them wide, this is what I mean. I mean that they have semi-major axes bigger than 1,000 astronomical units. Okay? These are really very wide systems. So something slightly less trivial is that you can derive the entire motion of this system just by writing down this function, this 2-body Hamiltonian. So it's the sum of the masses, m1 plus m2, divided by twice the semi-major axis. Once you have that, you can get all of the dynamics just by applying Hamilton's equations. There are 2 other things you need to know about Keplerian dynamics for this talk. One of them is eccentricity. So there's an orbit, and here is eccentricity. So these 2 stars don't, of course, have to go around each other in a circle. If they did, they would have an eccentricity of 0. But they tend to go around each other in something slightly elongated, or maybe very elongated. And so something that was very elongated would have an eccentricity of close to 1. Okay? So all of these binaries have the same semi-major axis, A, but they have different eccentricities. And eccentricity goes on a sliding scale from 0 to 1. Again, I don't mean to insult you with this, but this is going to be completely crucial for the rest of the talk. The final thing that you need to know about Keplerian dynamics is this thing called an argument of pericenter, which is a fancy way of saying how is the binary oriented. You see that this binary points to the east. This is the same binary on exactly the same orbit, exactly the same semi-major axis, exactly the same eccentricity. It's just oriented slightly differently. And this one is oriented slightly differently again. Just like Mercury processes around the sun, this is a change of this argument of pericenter, but it's just the orientation of the binary. Okay, that's all you need to know about Keplerian dynamics to follow the rest of the talk. Why should we care about these very, very wide binaries that are 1,000 AU apart, or even more? So there are 2 ways to answer this question. The first one is what I'll call the standard astrophysics colloquium justification. When you give an astrophysics colloquium, you say that either your subject will ultimately solve the habitability, aliens, and the origin of life, or you say that it's going to form structure, origin of the universe, right? Either the very small or the very large. And actually for wide binaries, both of these things are sort of plausible for the following reason. By the end of the talk, we'll hopefully understand something about how binaries form. And we don't really understand star formation in the first place. And in fact, there have been a bunch of nature papers in the last decade talking about whether planets can form around wide binaries, and whether those planets would be habitable, and so on. So, okay, that more or less justifies this part. On the right-hand side is maybe something a bit less, a bit more serious, which is wide binaries are in fact an extremely good test of gravity. So they're such wide systems that we really know, and they're such clean systems, there's no gas, there's no dissipation, that we really know how to solve the two-body problem exactly. And so if you want to look for deviations from Newtonian dynamics, this is a good place to look. In fact, if you've been looking at the archive over the last week or two, you'll have seen several papers claiming that the very, very widest binaries don't actually follow Newtonian dynamics. That's a completely different argument to this talk, but this is a good place to test gravity. And wide binaries historically were one of the things that were used to rule out the idea that dark matter was made of machos, massive compact little objects, black holes basically. Okay, so that gets you to the formation of the universe, and so I'm going to solve all of astrophysics in this talk, presumably. All right, so that's the first way to answer the question, but this is CIERA, and a bunch of you are theorists, and if I was an honest theoretical physicist, I would say this is why I study wide binaries. They're amazingly clean. There's no gas, there's no dissipation, I don't need to worry about all that nightmare. I can write down the exact solution to the two-body problem. Remember, that's the Hamiltonian that I showed you before, H0. And then I can talk about any perturbations, and I will do frequently for the next 45 minutes, and just put them all inside H1 and solve using perturbation theory. Okay? Also, you can spin this all up as a kinetic theory. Don't worry if you don't know what this equation means, but F is now representing not one binary, but an entire distribution function of binaries. And the secular, or galactic tides part of the talk, so section 2 of the talk will be about this term in this equation, and the stochastic, or stellar encounters part of the talk will be in this term. And so you can write down a kinetic theory of binaries in the same way as you could write down a kinetic theory for the gas in this room, in this form. There are also, as of GAIA, many observational puzzles. I'm only going to talk about one of them today. There are a bunch of things we don't understand about these ultra-simple systems, and some of them you can even write down your answer as a theorem plus proof style, which you don't often get to do in astrophysics, right? You can actually prove rather rigorously that this thing or that thing can or cannot be responsible for the observed behavior. Okay, so that's the motivation out the way, let's get into it. What are these observational puzzles? The one observational puzzle I'm going to talk about surrounds the eccentricity. So binaries that are circular have eccentricity of 0, binaries that are radial have eccentricity of 1. To motivate it, I'm going to need to tell you what is an eccentricity distribution. Now it's very straightforward, it's what it sounds like. How many binaries do I have at a particular eccentricity? And then I plot the probability of having a binary at a given eccentricity as a function of eccentricity. There's a special line on this plot, which is this black dashed line here. This is a so-called thermal eccentricity distribution, where roughly speaking you can think of probability of having eccentricity E as proportional to E to some power. If that power is just 1, of course you have a straight line, and that's called a thermal eccentricity distribution. The name thermal is because this is the distribution that you get if you just guess using statistical mechanics what the answer ought to be. Remember when you did statistical mechanics in your undergraduate, you fixed some quantity of the system, like the energy, and you randomized everything else, and you said, what's the most likely distribution that I get out? And you got the Maxwell-Boltzmann distribution if you're talking about gases or whatever. This is exactly the same thing. You fix the energy of a binary, or equivalently its semi-major axis, and you randomize all of its other degrees of freedom. And the result you get is an eccentricity distribution that's thermal. So suppose GAIA had never been there, and you had to just guess what is the distribution of wide binary eccentricities, you probably would have guessed this thermal thing. Alternatively, if I have more binaries, so I'm in one of these red curves, where there are more binaries at high eccentricity compared to thermal, and fewer binaries at low eccentricity compared to thermal, that's called a superthermal distribution. And I can parameterize that using this P of alpha with an alpha bigger than 1. Okay? And similarly, a subthermal distribution would be the same thing with alpha less than 1, because they have a deficit of binaries at high eccentricity. So that's all that we're doing with this eccentricity distribution. Now, this is what's observed. These are observations from Huang et al. Tokovinin found something very, very similar using GAIA DR2. You can do better these days. This is exactly the same distribution as a function of eccentricity. There again is the thermal distribution. And each of these different strips is for binaries of different semi-major axes, or different separation really projected on the sky, different separations, okay? So the widest binaries are these purple, brown, pinky kind of color ones, these ones here. So you can see that they're clearly superthermal. Okay? You have more binaries, so these are log of separation of 10 to the 3, 10 to the 4. These are 1,000, 10,000, even bigger binaries. And they have more binaries at very, very high eccentricity than you would expect compared to the thermal distribution. This turns out to be very difficult to produce. Nobody really understands where it comes from. Okay. So that is the puzzle. This is just another way of looking at the same thing. So as a function of semi-major axis, you plot this alpha, the best fit power law distribution. So when it was equal to 1, that would be the thermal, and everything above 1 is superthermal. So roughly, the wide binaries that I care about in this talk have probability of having eccentricity E proportional to E to the alpha, where alpha is something like 1.3. Yes?
What's the semi-major axis of an average binary, and what fraction of them are these
Right. So
wide binaries?
that's actually not, is also not completely understood. The classic thing everybody takes is something called Opic's law, where the probability of having a semi-major axis A declines like 1 over A. So at the highest semi-major axis, you have fewer binaries. But yeah, that hasn't been folded into this, but we're doing this at every single bin. And the other thing to say, yes, oh, I've got so many questions. Yes, first.
Oh, you can finish.
Yeah,
You
sure.
were finishing your...
I mean, I was also only going to say that if you're worried about small number statistics, there are hundreds of thousands of binaries in this sample. So it's not like you only have 3 binaries up at high eccentricity. Yeah. Yes, first.
So what observational effects are taken into account in the plot you just showed? Because I can very well imagine that the observational selection effects are actually going to change with your binary separation.
Yes. So the very wide, so these are resolved binaries in GAIA, the very widest ones. So you make some cut on the signal to noise of that. So I think they only look within something like 140 parsecs, or several hundred parsecs at least. You have to assume, so right, this is a statistical measurement. You're not really seeing the orbit because the orbit takes 1 million years. You're doing a statistical measurement. The key assumption is that the binaries are oriented isotropically. That's the major thing. Now I think that you can check that a posteriori. At least are they projected on the sky in a random direction? And the answer is yes, to very high accuracy.
Well, but it also depends on your velocity measurement.
No. So the way this is measured does not use the absolute value of any velocity. It uses the angle between the projected separation on the sky and the velocity vector. So it doesn't matter if you get the magnitude wrong, you just need the direction. And then you look at the angle and the distribution of those angles, it turns out gives you one of these eccentricity distributions. We can go into details about this later if you like. Yeah, okay, yes.
So maybe a slightly silly question, but other than we're doing astrophysics, what's the motivation for a power law distribution?
Haha, good question. Yes. I'll get a bit more into that later. It turns out that it works very, very well. If you do things dynamically to binaries, they always tend to be well fit by this, and I'll show you examples of that. It has to be increasing monotonically. If you think of it as, suppose I have a very wide binary. And I just form it at some separation. What's the probability that it ends up on a circular orbit? Almost 0. Reason being, I have to set it up so that the velocities are in exactly the opposite direction, and they're moving it exactly square root of gm over r. Any other configuration will give you something eccentric. So roughly speaking, there's just more phase space available at high eccentricity than there is at low eccentricity. That doesn't completely answer your question, but the extra part is just that power laws tend to work extremely well. Yeah, but we could do something more general, but it doesn't really matter here. Yeah, and actually, I will later on do experiments where I don't put in a power law to begin with, and it still ends up looking like a power law after some dynamical stuff has gone on. All right, good. So this is what the observations look like. This is the thing we're trying to explain. Why are the wide binaries superthermal? So there are 3 possible reasons why they might be superthermal, I would say. First of all, well, maybe they were just born like that. Maybe they formed superthermal. That's not really an answer. It's not a very satisfying answer, because then you have to talk about how did they form in the first place and why did they form with this superthermal distribution. The other thing is, you could say, well, I have no idea how they formed, but maybe because they're interacting with stars that are coming near them, those stars give them kicks, and maybe that produces a superthermal distribution. That would be these encounters. And finally, these binaries are so wide that in fact you have to account for the effect of the entire galactic disk acting as a perturber upon the binary, for reasons that we'll see in a moment. And so maybe that churns up the eccentricities, and maybe that can produce the superthermal distribution. I'm going to show you that neither this nor this can be responsible. That's the next two parts of the talk. Okay, so how does this work? What are the galactic tides? So Heisler and Tremaine understood this in 1986. They weren't looking at wide binaries, they were actually looking at a comet. This is not to scale, by the way. This is the sun, and this is a comet going around the sun. It's effectively a wide binary. It's exactly the same dynamics. And they realized that the entire tidal torque from the whole galactic disk over very long billion-year timescales could change the eccentricity of one of these comets. And in the case of the Oort cloud comets, that can make them come very radially so we can actually see them, right? So this is a sort of, what effectively this is a three-body problem. So I'm going to talk a little bit about three-body dynamics. So let me collapse the entire galaxy into a single point mass, so now the galaxy is just this green point mass here. So now we're talking about the hierarchical three-body problem, which there are people in this room who know it better than I do. So again, I have my red and blue binary. It has some semi-major axis A. And now let me add a weak perturbation, which is the green star here. And the green star is going to orbit around the binary. So the binary is doing its own little orbit, and the green star is orbiting around the binary. And the thing I care about is the evolution of this inner binary orbit. Semi-major axis, eccentricity, and these other angles as well. So this is a stable system, provided the green star is far enough away. It's not chaotic. And so we can solve for this evolution of this system using perturbation theory, where H0 here is the two-body Hamiltonian, the thing that I showed you before, which just tells you how this would evolve if there was no green star. And H1 is the perturbation due to the green star. What actually happens if you do this in practice is that you find this perturber is able to change dramatically the eccentricity, inclination, and so on under the right circumstances of the binary. So for instance, this binary might start out with an eccentricity. This is eccentricity as a function of time. Eccentricity close to 0. And that eccentricity grows and grows and grows, and it gets to, in this case, something like 0.7. And then it decays again, and it grows again. These are called Lidov-Kozai, or now von Zeipel-Lidov-Kozai oscillations. It turned out von Zeipel actually solved this in like 1870. And then it was rediscovered in the 60s by Lidov and Kozai. So this is a way to make the inner binary eccentric. You can already see where I might be going with this. Right? This is the inclination, so it turns out that the inclination and the eccentricity exchange oscillations. Don't worry if you don't know what that is. So how do I describe this mathematically? Well, I do that perturbation theory that I told you about. I treat the green star as a weak perturbation, and then I perform two averages. First of all, I average over the motion of the inner binary, and then I average over the motion of the green star as it goes around the binary. The rationale for that is that this is such a weak perturbation that on those timescales, it's not really doing anything. It takes lots and lots of repetitive orbits for anything significant to occur. So I can average over the timescales that I don't care about. When I do that, I get three conserved quantities. Remember your Hamiltonian dynamics, you average out something, you get rid of a coordinate, you get a conserved quantity as a bonus. So the semi-major axis A of the binary is constant, so the semi-major axis is not going to change. The angular momentum, which is the square root of 1 minus e squared cosine I is the inclination between the two orbits, will also be constant. And finally, more importantly, this sort of perturbation energy, this is that H1, that Hamiltonian, averaged, is also a constant of the motion. So this is 2 plus 3 e squared, 1 minus 3 cos squared I minus 15 e squared sine squared I cos 2 omega. Can you tell I've given this talk before? I don't expect you to remember that, but you're going to see something very similar to it in a moment. The point is that that's a constant of the motion. It's a conserved quantity. What that means is if you draw contours of this conserved quantity in this phase space of eccentricity against omega, remember omega is just how is the binary oriented, these contours are the black lines. But that's a conserved quantity, which tells you that every binary must sit on one of these black contours. So this is how the oscillations work. Maybe you start at 0.2, you follow this contour, you go up to something like 0.95, and you go back down, and so on. And these are the Kozai oscillations. And I'm just showing you it in phase space rather than as a time series. That's the only difference. Okay. But there's actually nothing special about that green star just being a star. I could now do exactly the same dynamics the same problem, but replace it with the full galaxy. So I take a simple model of the galactic disk, and I look at the potential due to that. And the solution in that case is 2 plus 2e squared sine squared I minus 5e squared sine squared I cos 2 omega. Look rather similar. Okay? In fact, more generally, you can do this without a point mass or without a galactic disk, and just some arbitrary axisymmetric tidal potential, and you get this thing. So I have a whole bunch of thesis chapters based on this, and this is just the special, these are just special cases of that general formula. All right. So, what have we learned? We've learned that if I put a wide binary into the galaxy is going to change the wide binary's eccentricity, small to large and small to large, and it turns out that takes about 1 billion years, typically, for the very widest binaries. Which sounds pretty long, but the galaxy is 10 billion years old. So for a bunch of the wide binaries, this will actually have been a significant effect. So we know what happens to one binary. So what happens to 100,000 binaries? So this is, if you see any animations in this plot, they were done by Sean Akmora, who's a grad student at Princeton. He's working with me and with Scott Tremaine and Eve Ostraker. And so every gray dot in this plot is a binary. And it's going to do exactly what I just showed you for one individual binary. It's going to go around a particular contour. This j is now just the square root of 1 minus eccentricity squared. It's just a change of coordinates. Don't worry about it. Just plotting something slightly different on the y-axis. So now I'm going to follow the evolution of, I think in this plot there are 10,000 or something binaries. And you're just going to watch what happens to begin with. So this is what the galactic tide does to this huge number of binaries. Notice that these contours are now becoming smeared out along the contours of the Hamiltonian that I showed you before. Okay, so the density of the binaries is becoming evenly spread out along those contours. Why is that? Well, let's just look at this patch here, the colored in patch. I've just painted individual binaries. The point is, all the binaries are going to do these Kozai type oscillations, but they do them at different rates. So the ones in red here go around on their loops a bit faster than the ones in blue. So you have a shearing motion where one part of the phase space is moving at a different rate to the other one. And so they get strung out. And if you just watch the patch, you see that they get strung out along those Hamiltonian contours. Okay? So that's what happens to a whole distribution. In other words, it turns this into this. If I now color in the whole thing, it turns, let's say I have lots of binaries in the red region and not so many binaries in the blue region, just for illustration, it's going to turn this into this. So this is what the galactic tide does. It takes a distribution of binaries and it churns them up until they're spread evenly along the Hamiltonian contours. Okay? And this timescale for this is something like 1 billion years. So that's all very nice, fun dynamics. You can write down a formula for how you get the final distribution. You don't need to do any calculations really, you just write it down. But what does that do to the eccentricities? That's the thing we really care about. Okay, so that was done in the full phase space where you have inclinations and this argument of pericenter and so on. If I get rid of all of that, integrate all of it out, how are the eccentricities changed? That's what I really care about. In this experiment, I've taken an initial distribution which is uniform. So the eccentricities here are the initial red line, and they're uniform. And the thermal distribution is this thing that's proportional to eccentricity. Now, if you use that formula that I just showed you, it predicts that the final distribution will lie along the blue line. Let's see what happens. The whole thing sloshes around, and lo and behold, it works. In other words, I started with the red line. I started with something that's uniform, severely subthermal, and I produced something that's still subthermal, albeit a bit closer to thermal. Critically, what I have not done is produced a superthermal distribution. So I can't explain the observations with something like this. Similarly, if you were to take an initially superthermal distribution, so this black line here is the initial distribution now, the theory tells you that it should ultimately lie along the red line, and if you watch what happens, it ultimately lies along the red line. So I've taken an initially superthermal distribution. It reaches a steady state that is still superthermal, but a bit less superthermal, a bit closer to thermal. Again, that doesn't really answer the question, because how did I form the superthermal distribution in the first place, right? We're back to formation. Now, every time I would give this talk, somebody would ask, is this a theorem? So I published a paper in which I just did a bunch of numerical examples, so many numerical examples that I was confident that this was the answer. You can't start with something subthermal and produce something superthermal. But it turns out that you can actually prove this generally. And you can prove it for all times, you can prove it for any initial distribution, and you can prove it for any model of the galactic disk. It doesn't matter what you put in, effectively. You will never start with something that's not already superthermal and produce something that it becomes superthermal. In other words, this thermal distribution is a kind of barrier across which you're not allowed to cross. The proof of that, yes, go ahead.
Would that hold for different perturbations than like a galactic disk perturbation?
Any Hamiltonian perturbation.
Okay.
Yes. I'll show you the stellar scattering is not a Hamiltonian perturbation, and I'll show you what that does in a moment. Yeah. So it would work, if the galactic disk was much fatter or whatever, and it works all times. The way you prove that is, yes?
Do you fix the initial inclination?
I am assuming that the binaries are born in random directions, isotropically.
Oh.
So the inclination is uniform in cosine I. The way you actually prove this is basically Liouville's theorem. Remember your Hamiltonian mechanics again from undergraduate, where you remember that a phase space flow is incompressible. Right? Phase space acts like water. You can't squish more phase space fluid into a particular location. It turns out that to cross the thermal barrier, to go from subthermal to superthermal using galactic tides, would actually contradict Liouville's theorem. So you can see the paper if you want to know the details of how that works, but effectively this is as close as you can get to a cast iron proof that that is never going to be the answer. Okay, how am I doing? So, to summarize, galactic tides are efficient drivers of eccentricity evolution for individual binaries on timescales of 1 billion years or so. They can maintain, but they cannot themselves produce the observed superthermal distribution. So that means that we can go back to this slide and we can cross out galactic tides. And so we move on to the encounters. What do I mean by encounters? Here's a wide binary. Wide binaries are sort of tortuously slow in their orbits. They're very, very lethargic orbits. That's because they're so far apart that their orbital velocity is something like 1 kilometer per second. Okay? Meanwhile, they're sitting in this bath of other stars. They're just somewhere in the galactic disk, and they're sitting within this bath of other stars. Those stars, relative to the binary, have a velocity dispersion of something like 30 kilometers a second, much, much faster. What that means is that when a star comes near the binary, it just shoots straight through. Okay, so this is an impulsive encounter. And in fact, it's not just one star, of course, but there are a bunch of stars all over the place, and they're all flying through the binary at all times. These encounters, individually, they turn out to be weak. So they're impulsive, that is fast. They're weak. They're isotropic, there's no preferred direction. And they're penetrative, which means that the most important ones actually pass straight through the binary. Okay? I don't need to worry about the ones that are very, very distant, just the ones that really come through the binary. And plenty of them do. I don't know what happened to this one down here. Doesn't seem to obey the... Maybe Mond can explain that one. All right. So, every encounter... Yes?
Do we know the radial distribution of these binaries from the galactic center as a function of simulation?
No. That is something that everything in this catalog was just all lumped together because it was in the solar neighborhood within a few hundred parsecs. The data is always getting better, and so you can start to do distributions as a function of where you are in the galaxy. And yeah, I would like to see that, but it hasn't been done yet. So each of these encounters with one of the green stars is weak. What that means is that it changes the semi-major axis of the binary by some amount delta A, which is small compared to A. And it changes the eccentricity by some amount delta E, which is small compared to E. And so you good theoretical physicists in the audience should know that I'm now going to use a Fokker-Planck equation to describe this dynamics. So F here is the distribution function of binaries in terms of their semi-major axis and eccentricity. In fact, I'm not now going to use eccentricity. I'm going to use a different thing, eccentricity squared, this curly epsilon, or as I have taken to calling it, square-centricity. The name has yet to catch on. What this means is that a thermal distribution, remember thermal distribution was proportional to eccentricity. If I do it in these variables, it just doesn't depend on the eccentricity squared. Okay? So a thermal distribution has no dependence on curly epsilon. It turns out those are the nice coordinates with which to do this problem. So F is how many binaries do I have at a particular semi-major axis and a particular square centricity. And this Fokker-Planck equation tells you how F evolves under lots of little nudges from all the passing stars. For the experts in the audience, this A here, this is a drift coefficient in semi-major axis. It's positive, which means that Hege's law is obeyed, which Hege's law tells you that if you have a very wide binary and you kick it, it gets a bit wider on average. It can go smaller, but on average it will get wider. And so binaries get wider and wider and wider and wider. And eventually they're so wide that the galactic tide I was telling you about before actually rips them apart, which is just like ionization of your hydrogen atom. Okay? It gets so loosely bound that a little nudge, it's gone. So that's one way to destroy wide binaries. Okay, but this equation describes the evolution of binaries under all of that static. Again, Shonak did this calculation. This is the solution to that equation where I'm just sampling a bunch of binaries. For illustration, I've taken some really silly initial distribution. All the binaries here have semi-major axis of 10 to the 3 AU. And so I've taken some with eccentricity squared of about 0.3, some with 0.7, and some with 0.5. And now we're just going to watch what happens. So every point is being kicked by all different stars all the time, and they're undergoing some kind of random walk. And the Fokker-Planck equation is going to describe the distribution underneath that random walk. Okay. Notice, we're now at about 5 gig years. Notice that the red clump that we had over here has now spread more or less uniformly across in eccentricity. And the blue clump that we had over here has now spread to the left and then getting towards being uniform. Remember, uniform, if there was no dependence left to right, that's thermal. Thermal distribution doesn't care where you are in this square centricity variable. Meanwhile, the whole distribution is on average moving up. That's the Hege's law. Wide binaries get wider, so they go to larger semi-major axis and larger semi-major axis. And in fact, there's somewhere, it's off the top of this plot, but there's somewhere where they're so large that we actually remove them from the simulation because those ones would get unbound, ionized. Okay. Skip this. How long does this take? The typical timescale for this random walk, whether it's in the semi-major axis direction or in the eccentricity direction, turns out to be the same. And it's about 4 gigayears at 10 to the 4 AU. So that's very similar to the estimate I showed you before for the galactic tides at 10 to the 4 AU. But it depends on semi-major axis in a slightly different way. So I can make this plot, which is roughly speaking, this is semi-major axis on the x-axis, and the time scale for something to happen on the y-axis. And so I have the stellar encounters are in green and the galactic tides are in orange. So if you're between 1,000 and a few times 10,000 AU, the shortest time scale is the one for the stellar encounters, so you can kind of ignore the galactic tides and just do stellar encounters. Meanwhile, if you're between several 10,000 AU and several times 10 to the 5 AU, the galactic tides are more important, and you can ignore the stellar encounters. So roughly speaking, section 2 of this talk applied to this regime, and section 3 of this talk applies to this regime. We don't actually know what goes on in between. If somebody would like a summer project to just brute force numerically work out what happens in the middle regime, I would be amazed if it does anything other than what I'm going to tell you, but maybe it does. Okay, so those are the different regimes. This is again what happens to stellar binaries. This is just to show you the ionization. So now I've taken a load of binaries, 10 to the 3, sometimes at 3 times 10 to the 3, 10 to the 4, and so on. And we're just going to watch them evolve. Notice that the blue ones are going to get destroyed. They get destroyed if they hit this line. That's the ionization, whereas the red ones are mostly going to survive. So it goes quite quickly. Blue's gone, green is gone, orange is more or less gone. And after 10 gig years, more or less only the red ones that are left. Okay, the point is just that the things that are very wide, they evolve fastest because it's easier for the stellar encounters to hit them. They have just a bigger cross section, so they evolve fast. And as soon as you get to the dashed line, you're out the simulation. All right, so that's how ionization is a function of time. Back to eccentricity. What does this do to the eccentricities? So here, I've taken an initially superthermal distribution. That's the thing in blue. And I'm going to see what happens to it over time. It's actually going to be much less dramatic than what happened with the tides. So this is just under the effect of stellar scattering. And you see that it just very gradually walks its way towards thermal distribution. In fact, these are the binaries that have 10 to the 3 AU initially. So they, in 10 gigayears, they only end up on the red line. They don't actually have time to get all the way towards thermal. But if you run it for 15 gigayears, they actually do become thermal. Meanwhile, if you were to take any other distribution, run it for long enough, it eventually becomes thermal. Okay? So you do numerical experiment after numerical experiment, and you find that the solution is always things tend towards thermal. And they never cross from subthermal into superthermal. And you can say, well, is this a theorem? And the answer is yes. You can prove that stellar encounters will always drive any eccentricity distribution towards thermal, and therefore that encounters cannot be the responsible things that produce the superthermal distribution. The way you do that is technically you take the distribution, you split it into a part that's thermal. This doesn't depend on eccentricity squared, and a bit that's the rest. And then you do a kind of H theorem. You show, using the Fokker-Planck equation, you show that the norm of this non-thermal piece always decreases. And in fact, it only ever stops decreasing once it's zero, once you produce a thermal distribution. So it's sort of, thermal is a kind of maximum entropy state. Now, you might say, well, Chris, that's completely obvious. Why are you bothering with all this fancy mathematics? If I take some system and I just hit it many, many times, of course it's going to look uniform. And of course it's going to be thermal. Then you think about it a bit longer, and it's actually not obvious. It would be obvious if you allowed me to fix the energy or fix the semi-major axis of the binary and then hit it a lot of times. Then I would say there's absolutely no question. It has to be thermal. But remember, these binaries are not fixed in semi-major axes. They're all drifting in semi-major axes. And so if you look at a fixed semi-major axis, I say I only care about binaries that are between 3,000 and 4,000 AU. The set of binaries that are in that range today are not the same binaries that were in there yesterday, and they will not be there tomorrow. But the point of this is that even at a fixed semi-major axis, the distribution tends towards thermal, even though it's not the same binaries today as there was yesterday. Okay? So it's less trivial than it sounds. Okay, so to summarize, you can work out the effect of stellar encounters because they're isotropic, impulsive, penetrative, and weak. You can use a Fokker-Planck equation, in other words. They always drive a distribution towards ionization in semi-major axis and thermal in eccentricity, and these two things take the same amount of time, roughly 1 billion years, 10 to the 4 AU. And so the encounters cannot be responsible for the observed distribution, which means we can go back to this slide and we can cross out encounters, which means that there's only one thing left. Unfortunately, we're back to the start, which says that the binaries simply must have formed this way. So throughout the talk, I've been completely agnostic as to how binaries form, because it's a horribly messy problem and I never wanted to get into it. But it's forced upon you. The binaries simply must have been formed that way, and so how were they formed? So for the last 10 minutes, I'm going to tell you what this implies about binary formation, how you might test that and make some predictions for future data releases. So, formation. Let me get rid of the rest. There's only one culprit, and it's formation. There have been a few different papers on how wide binaries might form. Not actually so many, it's a hard problem. One of the important ones was by Rippert and Mikula. They looked at something called the dynamical unfolding of hierarchical triples. Think of it this way, if you form stars inside a cluster, then very early on in their life, there are lots of 3 and 4 and 5 body chaotic encounters, and that can produce very wide triple systems, it turns out. And you could think of a binary as actually a closed binary plus a third body. From a distance looks like a binary. And so you could ask, what is the eccentricity of that very wide binary? That's one way to form these wide binaries. They can form, this should not say superthermal, this should say highly eccentric. They can form things that are very, very highly eccentric, but it turns out that they don't produce something superthermal. And in fact, in Huang's GAIA data, it's not the case that the binaries that I've been telling you about are certainly not triples, but we know that triples are not the thing that's producing the superthermal distribution. They're not a dominant source of error. Probably 20% or something of the observed binaries are actually triples. But it turns out that if you fold that in, that would make things more thermal rather than less. So that can't be the explanation either. In other words, you can rule out this reperpendicular idea as being the main thing that forms binaries. Penarubia, a couple of years ago, also had a cute idea, which is that you could form binaries in stellar streams. You take a globular cluster, or a dwarf galaxy, that falls into the Milky Way. It gets stripped into a long string of pearl, like a string of stars, like a string of pearls. And each of those stars, if you take the two pairs, you can ask, are they bound? And you can form very loosely bound, in other words, very wide, binaries that way. Unfortunately, if you simulate that, you find that the distribution is subthermal. See, there's not enough binaries at very high eccentricity. And so you can also rule out that as being the main thing that formed wide binaries. Not that anybody was really claiming that that was the main thing. That's obviously, there are not so many streams in order to do that, but that also doesn't help with the problem. There have been one or two others that I won't go into. I will leave you with this one, which is a paper that I was on by CIERA at the IAS. And so this is going to explain why this figure has been sitting there the whole time. We did something that's very, very crude and very, very hand-waving, but actually turns out to be remarkably robust to the parameters that you put in. And so I think it's at least hinting at the answer. So what you do is you say, well, stars form in some kind of turbulent interstellar medium. People simulate turbulent interstellar media, and then they take the parcels of gas and they measure what is the velocity distribution of, if I take a particle of gas here and one here, what is the velocity separation between the two, and then let me do a distribution function of that separation. Okay? And it turns out it looks something like this in the simulations. It looks vaguely kind of Maxwellian. These are for different choices of the parameters, different distances, blah, blah, blah. It's not actually going to make much difference at all. Now you close your eyes and you click your fingers and you hope. You say, instantaneously out of this gas, I'm going to form a load of stars. And I'm going to assume that the stars that I form have precisely the velocity distribution that the gas had that they just formed out of. And now I'm going to take two random stars and I'm going to ask, are they bound? And if they are bound, what's their eccentricity? And then I'm going to do it for all possible pairs of stars and I'm going to work out the eccentricity distribution. So my contribution to this paper, that's what I just said, my contribution to this paper was that if you do that exercise, you can just write down the final distribution in one line. It's just this integral here. All it depends on, this is probability of having eccentricity E, all it depends on is your choice of f of u. F of u is this velocity distribution of the gas. It turns out that it doesn't matter too much what you choose that to be. You very often find something that's highly superthermal. So this is the result of using this formula. You get probability of having eccentricity E as a function of E. Here, the black dashed line is the thermal distribution. The GAIA is not on here. Let's stick to this one, sorry. The blue dotted line is the GAIA superthermal distribution. And the black lines are two results of using this formula here. So you produce something that's significantly more, perhaps, superthermal than GAIA. That's not a problem. I'll tell you why in a second. If you look at the reperpendicular, which is the red line, it's clearly not close to superthermal, and you will never be able to produce this excess at high eccentricity. Why is it not a problem that we produce something that doesn't look like the GAIA data, but has produced something even more superthermal? The reason is that we know that the binaries didn't just form. I've spent 40 minutes telling you how they evolve over time. So if they formed like this, then the effect of the galactic tides and of the stellar scattering over the subsequent 10 billion years or something like that will be bringing them down towards thermal over time. And so if they had started off on the blue line, they would not look like the blue line anymore. They have to form more superthermal than they are today. Okay, so this solves that problem. Okay, but obviously this is an extremely crude model of star formation, if you can even call it that. Much more work needs to be done. But that's where we are. So I'm plenty of time, I think, so let me summarize. And then I'll take some questions. So wide binaries are a theorist playground, which is really why I'm interested in them. We have this amazing data from GAIA. The data is getting better. There are a bunch of observational problems, including ones that I haven't told you about today, that we simply don't know the answer to. In particular, there's this superthermal distribution, which says the probability of having eccentricity E, it grows like e to the 1.3, roughly speaking. we can rule out, provably, that the galactic tides or stellar encounters are the things that produce that distribution. And so that tells you that the distribution must be a result of formation. And so you can rule out a bunch of different formation mechanisms of why binaries used in this. In the future, the thing I just told you, you can put on a quantitative basis and you can say, let me now bin the stars by age. Okay? Everything I just did was for all the stars in every distance, every age, lumped together into one measurement. But you could say, well, all the binaries aren't 10 billion years old. Some of them are 6 billion years old. Some of them are 4 billion years old. And so you can bin them like that. And what you should find is that this alpha parameter should decrease with age. Okay? That's a prediction for theory. Another thing would be, coming back to a question that somebody had in the audience earlier, where the binaries are in the galaxy is also going to change this alpha. So imagine that you're in the thick disk of the galaxy, which means that you're not orbiting in the plane, but you're orbiting also up and down to quite an extent. It turns out that if you're in the thick disk compared to the thin disk, the galactic tides are just as strong. It makes very, very little difference if you're on the thick disk compared to the thin disk. But the number of stars around you is much lower, right? Because the thin disk is much more diffuse. So the effect of the stellar encounters is going to be lower. And so the relative importance of galactic tides and stellar encounters is a function of where you are in the galaxy and what orbit you're currently on, the galactocentric orbit of the binary. That, believe it or not, is also something that can be tested pretty soon, probably with GAIA DR4. I will leave you with that. I'll take any questions. Thank you very much for listening. Anyway.